Hello everyone, welcome to the next lecture of bipolar junction transistors. We are covering this chapter number 6. So in the last lecture we talked about these large signal equivalent circuit models of a bipolar junction transistor when it was being operated in the active region. We also looked at its actual physical structure of a transistor. Today we are gonna delve more deeper into the saturation region operation of the bipolar junction transistor. Right. Okay. So here are the quick comparison of the modes of operation between MOS, FET, and BJT. Kind of a summary of what we have discussed by far now. So if you remember, again, kind of making a quick comparison in between MOS, FET, and BJT, especially differentiating in between active and saturation regions. For a MOS FET, if you remember, we have three regions of operation: cutoff, triode, and saturation. And we were saying that saturation, kind of using these words interchangeably when discussing the amplifiers, that we were saying that the saturation and the active regions are the same. Then to use MOS FET as an amplifier, we can operate that in the active or saturation region. The same region of operation, to use this as a switch, we can operate that in between cutoff and triode region. Now let's look at the BJT. BJT has three modes of operation. One is called as a cutoff, active, and saturation. Please again note that, and I have been making this point so many times over the course of these lectures, that the active and the saturation modes of operation in bipolar junction transistors are not the same. Unlike MOS FET, right? Saturation has a different meaning in BJT as compared to MOS FET. So again, if we want to use BJT as an amplifier, and we will discuss the amplifier operations of the BJT in much more detail later, we will operate the transistor in the active region. Active region is the one where our emitter base junction was forward biased and our collector base junction was reverse biased. And to operate that as a switch, we can operate in between cutoff region and a saturation region. For cutoff, our emitter base junction and collector base junction were both reverse biased. And for the saturation, our emitter base junction needs to be forward biased and collector base junction should also be forward biased. So this is the difference in between saturation and the active region. The emitter base junction should be forward biased in both the regions, whether it is being operated in active or saturation region. However, when the collector base junction is forward biased, it is operated in the saturation region. When it is reverse biased, it enters into the active region. And this phenomenon we are going to discuss in more detail today, that how it transfers in between the saturation and or the active region, saturation or the active region, transfer in between these two regions when our collector to base junctions moves from reverse bias to a forward bias condition. Okay, so let's talk more about the saturation mode. So we know that for an NPN bipolar junction transistor, we can operate that in the active region when our collector to base junction will be reverse biased. And in order to make that happen, right, we want to make sure that our collector to base voltage should be greater or equal to 0. This is what we have discussed by far now, right? Our collector should be at a higher potential than the base, then our junction will be reverse biased. And again, this 0 volts over here assumes that diode is an ideal diode, neglecting kind of a barrier voltage that we need to overcome to move it into the active region. Now we are going to discuss that barrier voltage as well, and that value of the voltage that we need to overcome to move it in between the forward and the reverse biasing. So this is what we discussed, and we know that from the diodes and the p-n junction chapter number 3 studies as well. For a real p-n junction model, for the conduction to occur, we need to overcome this barrier voltage, and our forward biasing will happen at a specific voltage, right? So this was the exponential model of the diode where we have this something like this, right? So this was the voltage. Now this voltage that we need to overcome the barrier, the depletion region voltage, over here it can vary in between 0.4 to 0.7, 0.8 volts, depends on a lot of factor, the type of the semiconductors that we are making, the doping levels, the impurities, which type of the trivalent or pentavalent impurities that we are using, which type of a semiconductor we are using, whether we are using silicon or some other material. So this value depends on a lot of factors. Okay, for simplicity, we're going to assume over here for this theoretical analysis, we're going to assume it to be 0.4 volts, that this is the value of the voltage that we need to overcome to forward bias either the emitter base junction or the collector base junction, which is true. Okay, then so important thing is that, so this thing that we were, the initial condition that we were initially saying, that in order for the collector base junction to be reverse biased, our collector to base voltage should be greater or equal to 0. This will no longer be true if we will assume to be a real model now, right? So if we will assume this to be a real model, this means that my voltage across the collector to base should be greater than minus 0.4 volts to make it reverse bias, right? Just to make the thing slightly more easier to understand, right? So if we have a, let's say we have this NPN transistor, emitter base collector, right? So in order to forward bias, this base to collector junction or collector base junction, our VBC should be greater than 0.4 volts, right? So in order to reverse bias it, our VBC should be less than 0.4 volts, right? So I can easily write this VBC as VCB should be less than minus 0.4 volts. This is a reverse bias condition. So this means that when my VCB is greater than minus 0.4 volts, it will be forward bias. So this is the real, this is when we assume the PN junction to be a real model and not an ideal model. Okay, right? So this is this condition, that our collector to base voltage should be greater than minus 0.4 volts. And when this is true, then our collector to base junction will be reverse biased and we will still be in the active region and not the saturation region. Okay, here's our VI characteristics for the NPN transistor. Again, this is our collector current. This is that collector to base voltage, this voltage that we are just talking about, right? So we just saw that for this real diode model or a real PN junction model, our collector to base voltage needs to be greater than minus 0.4 volts to keep it forward biased, to keep it reverse biased actually. Okay, so this is our collector to base voltage, and so we saw that as long as our collector to base voltage is greater than minus 0.4 volts, our collector to base junction is reverse biased. And as soon as your collector to base voltage becomes less than minus 0.4 volts, the collector to base junction becomes forward biased. Yeah, sorry, over here, yeah, this should be forward bias and that was reverse bias. Okay. So we can see that when our collector to base voltage was less than 0.4 volts over here, our transistor was, our collector to base junction was reverse biased. This means that we are in the active mode. So this is our active mode of operation till this point till this point. And what will happen after that? After that, what will happen is as our voltage will reduce more, as our VCB will become less than minus 0.4 volts, right? So this means that our VBC becomes greater than 0.4 volts, right? So our collector to base junction becomes forward biased. And when our collector to base junction becomes forward biased, it will enter into the saturation mode. And we will realize that when it will enter into the saturation mode, our current will decrease sharply, exponentially. And we will see why this current will decrease, okay? Okay, so we discussed that our collector current is independent of this collector to base voltage as long as this junction is, collector to base junction is reverse biased, or the value of the VCB is greater or equal to minus 0.4 volts, right? Okay. And then we saw that as we decrease this value further, as we go down below this value, our current will sharply decrease as our collector to base junction will start to conduct. and our collector to base junction will become forward bias. And now we are going to talk about why this current will decrease, right? So let's see why this collector current decreases. All right, so here is this is the equivalent circuit model that we discussed in the last lecture, right? And okay, so here's our base terminal, emitter terminal, collector terminal. This is a collector current. This is the diode, the p-n junction diode in between the base and the emitter. This model is a common emitter model. And our emitter to base junction is forward bias here, and the collector to base junction is reverse bias. Since our collector to base junction is reverse bias here, right, so there's no conduction in between that collector to base junction, so we kind of assume this to be an open circuit. Now when this collector to base junction will become forward bias, what will happen is now that p-n junction will also gonna start to appear, right? So we are gonna include a diode over here. So this translates to the circuit. Again, we have an emitter, common emitter, a base, a collector over here. This is our biasing voltage, VBE, and our IB current is flowing here, our IC current is flowing here. This is the value of the collector current that was flowing initially, and now it will change when our collector to base junction will be forward biased, right? So we saw that over here, our collector current will change in the saturation mode, right? So this was the initial current that was flowing through that p-n junction, or this was a constant current that was flowing that was controlled by the base to emitter biasing voltage. And this is a new diode that will appear, right? So what will happen is, as the transistor will enter into the saturation mode, so this diode will conduct or not conduct, or how much it will conduct. So this is the bottom line of the circuit. When our collector to base junction was reverse biased, this diode was not conducting, it was open circuit, and we had this model. As soon as the collector to base junction becomes forward biased, this diode will start to conduct, and this current will start to increase. And this is how we are going to determine when this current will increase, what will happen to IB, and what will happen to IC. Okay, so let's look at the current through DB and DC. All right, so our current through this collector to base junction, again, when our collector to base junction will become forward bias, we have this diode DC will appear for that p-n junction. And if we look closely over here, the value of the current value of this, it is composed of it kind of depends on the two things. One is this ISC factor, which is again the scaling current for this p-n junction, and other is a biasing voltage of the collector to base junction, VBC, right? So depending on this biasing voltage, we are going to figure out how much current that is flowing over here, right? Again, you have something like this, characteristics of a p-n junction diode, IN voltage. So depending on the voltage level, our current will change. So that amount of the current will depend on how much is the biasing voltage that is applied at the collector to base junction, which is equal to VBC. All right, now let's assume that our transistor just enters into the saturation mode, right? So let's say it will start to enter into the saturation mode. What is going to happen now? So as soon as it will start to enter into the saturation mode, we're going to have this diode appear here. When this diode will appear over here, we are going to have a positive current that is going to flow into this branch through this diode DC. And when we are going to have a positive current that is going to flow through this, if we want to keep the current that is flowing through this p-n junction through this diode because of this biasing voltage the same, this means that our IB needs to be increased. Now my base current will increase. So if I will want to make sure that since my current through this diode DB will be the same because I have the same biasing voltage applied, and the scaling current over here ISB will be the same, if this is true, and I am going to have a positive increase in the current through the diode DC, this means that my base current will increase. Having the same thought process here, if our current through the diode DC will increase, right? If this current through the diode DC will increase as the collector to base junction becomes forward bias, assuming this current will remain the same, which depends on the scaling current over here and the base to emitter voltage that we are not changing, assuming this current to be the same, right? If we have a positive increase in the current through the diode DC, our collector current will decrease to keep this current the same in this branch. So the impact of forward biasing the collector to base junction will be that our current through the diode DC will change, and the amount of that change will depend on the biasing voltage VBC. Now, as the current will start to flow through this diode DC, our base current has to increase to cater for this increase in the current through the diode DC, and our collector current has to increase to cater for this current that is flowing through the diode DC. Okay, so our new collector current can be given by using this equation, right? We can also easily write this as IS E VBE over VT equals IC plus ISC E VBC over VT, right? So we can easily find out by IC will be the subtraction of the two, right? Okay, so IC will be the subtraction of the two. So if we look at this equation closely, that the more and more forward bias, as we apply more and more VBC or the forward bias voltage value, as it will increase, our current through this branch will increase. So this means that this current will increase, right? So this current is going to continuously increase. When this current will continuously increasing, our current IC will continuously decrease till a point will come, it will reach down to 0. And this is the same effect that you can see over here, the saturation mode of operation. As your VCB falls below minus 0.4 over here, the collector current starts to decrease. And now what is happening, as you are falling, as your value of this VCB is decreasing from this point onwards, the collector current value is decreasing till it becomes 0. And why is that happening? Because the current that is flowing through this diode DC is increasing. This value of the current is increasing, so the total value of the collector current is decreasing. Now let's look at the base current. So we just discussed that in order, when our collector to base junction becomes forward bias and when a positive current flows through this branch, this means that in order to keep the value of the current through the diode DB the same, our base current needs to increase. So our new base current will become equals to this ISB E VBE over VT plus ISC E VBC over VT, right? So this is the new value of the current, which will be the summation of the two currents. So what is happening is, as we are moving away from the active region into the saturation mode, our collector current is decreasing and our base current is increasing. All right. So this is the value of the base current, right? So this is the value of the base current. This is the value of this ISB, which is equals to IS over beta. We saw that earlier, right? So this is ISB. This ISB equals IS over beta. All right. So this is a base current. So our base current will increase and our collector current will decrease. All right. We can also just find out, if we take a ratio, we can find out the value of the IC over IB. If you remember, this ratio of IC over IB was equals to beta, common emitter gain factor, IC over IB. Now, interestingly, if you will realize now is, right, so we, from earlier analysis, we know this thing. Now, interestingly, we can see that as we are moving from the active region into the saturation region, as our VBC potential is increasing, our forward biasing potential is increasing, our IC is decreasing, our IC is decreasing, IB is increasing, so our beta will reduce. So our current gain in the saturation mode of operation will reduce, right? So in the saturation, in a saturated BJT, thus this ratio will be lower than the value of the beta, because our base current is increasing and the collector current is decreasing. And this is what we discussed earlier, that as we are moving away from the saturation region, this is our transistor is going more and more deeper into the saturation region, where the current through the diode DC is increasing, and till a point will come when it reaches 0. when it will continuously increase, then the collector current will become 0. All right. Right, so as this potential is increasing, our BJT is driven more deeper into the saturation region. So we found out that our new beta value in the saturation mode is different than the beta value in the active mode. Right, so our beta value of the saturation region is different than the beta value of the active region. Why? Because beta is defined as IC over IB ratio. And for the saturation mode, the collector current will reduce and the base current will increase depending on the biasing voltage VBC applied at the collector to base junction. Okay, so now, we are going to call that beta value for the saturation region as forced beta, right? So this VBC is VBC, that biasing voltage, right? So this is forced beta. This is the beta at the saturation value, and this will be less than our normal beta value, which was for the active region of operation. All right, so interestingly, how we can find out if our transistor is operating in the saturation region or active region, right? So if you remember the MOSFETs as well, it was very important to figure out whether our transistor is being operated in the active end or the saturation in different modes of operation. Where active in the MOSFET, active and the saturation was the same. In BJT, they are not. However, it is very important to figure out exactly in which region of operation our transistor is operating. So we can use this entire theory of forced beta to figure out whether our transistor or a BJT is operating in the saturation region or the active region of operation, different modes of operation. Okay, so there are two conditions that we can use to figure that out. The first one is we know that our collector to base junction will be forward biased for saturation region, right? And in order for the collector to base junction to be forward biases, our collector to base voltage value, our base to collector voltage value should be greater than 0.4 volts, right? So if our base, this is for the NPN. So if our collector to base junction is forward bias and is greater than 0.4 volts value, then this means that our transistor is being operated in the saturation region. The second thing that you can try out is to find out this ratio over IC over IB. If you can find out the ratio of IC over IB and that turns out to be lower than the beta value of the transistor, then you can say that that transistor is being operated with those current values in those certain conditions is being operated in the saturation region and not the active region of operation. Okay, so if we have to find out this collector to emitter voltage value of a saturated BJT, so how we can find this out, right? So if you want to find out the potential difference in between collector to emitter and the saturation region, so we can find this out by VCE saturation as all right, so it will be VCB collector to base voltage that we apply minus VBE base to emitter voltage that we apply, right? So it will be the difference of these forward bias voltage of the emitter to base junction and the collector to base junction, right? So emitter to base junction and the collector to base junction, the forward bias values of these, right? So this equation can also be written as, right, if we will just take an inverse, VBC plus VEB, so VEB minus VBC, depending on how you write down the polarities or how you connect the power supplies to the transistor, right? So it will be the difference of these forward bias voltages of the emitter to base junction and the collector to base junction. Okay, so another important thing by looking at this, if you want to look at these values or the saturated value of the collector to emitter voltage, since we know that our collector to base junction area is much larger, right? If I will go back to the structure of this transistor, our collector to base junction area is larger than the emitter to base junction area. If we know that thing to be true, so this means that our forward bias voltage for the collector to base junction will be smaller, right? Because we have a much larger area. So the required forward biasing voltage for the collector to base junction will be smaller as compared to the emitter to base junction by a value of 0.1 to 0.3. Okay, So this is our saturation. So this is a typical value of the saturation region of the collector to emitter saturated values. It lies in between 0.1 and zero point 0.3 volts. And we typically we see that and kind of another thing to remember, again, that depends on the specific values, and the condition depends on many factors, on the specific transistor types, and the impurities and the doping levels and a lot of other factors. For simplicity over here, we can assume that it lies in between 0.1 to 0.3 volts. So at the edge of the saturation, our value of the VCE saturation is zero point 0.3 volts, and we will say that when our BJT is in deep in saturation, our VCE saturation value is 0.2 volts, right? So this is the edge of saturation over here, right? So this is our edge of saturation, and this is very deep into saturation, somewhere over here. So the collector to emitter voltage value at the edge of saturation is 0.3 volts, and very deep into the saturation is 0.2 volts. Okay, so this is our lecture today. In the next lecture, we're going to talk about the PNP transistor and discuss more about the symbol of the transistor. We will do more examples as well. Again, in this lecture, we talked about how we can operate the transistor into the saturation mode. For saturation mode, our collector to base junction needs to be forward bias. And in order to forward bias the collector to base junction, considering an NPN transistor, we can see that, so we did this analysis over here, right? Our base to collector voltage value should be greater than 0.4 volt for this NPN transistor, and that will make the transistor or the collector to base junction forward bias. And when that will happen, the transistor will enter into the saturation region over here. And when the transistor will enter into the saturation mode, we are going to have a diode. Our equivalent circuit is going to have an extra diode in between the base and the collector terminals, and a current is going to flow through it. When a current will flow through this diode DC, in order to have a same current flowing through the diode DB, our base current needs to increase. And in order to have a same current that is flowing through this branch, our collector current needs to decrease. So our overall effect that will happen is our collector current is decreasing and our base current is increasing, and this will make the beta value in the saturation mode to be smaller. So we call this beta value as a forced beta, right? So our forced beta is always less than the value of the beta, and we can use these two conditions to find out whether the transistor is operating in the saturation mode or not. If IC over IB value is lower than the value of the beta for the active region, this means that it is in the saturation mode. And or if our collector to base voltage, or if our collector to base junction is also forward biased, right, then this means that it is also being operated in the saturation mode. Okay, so with that, we are going to end our lecture today, and I will talk with you guys in the next lecture. All right, thank you so much. Have a good day. Bye bye.